Welcome back to another video on design of experiments and analysis of variance. The main problems we need to address through proper design of experiments are bias and variance. Bias is when the results of an experiment are systematically pushed in one direction, usually because something in the way we designed or conducted the experiment is influencing the outcome. To eliminate bias, we can include a control group for comparison. Use randomization to assign treatments, so we're not picking who gets what based on assumptions, and sometimes apply blinding, where participants and even experimenters don't know which treatment is being used, so their expectations don't affect the results. Variance, or sampling error, is the natural variability in data that can make results unclear or less reliable. To reduce this variability, we use replication, running the experiment multiple times so we get a more accurate average. Balanced designs, making sure each treatment has the same number of observations so no group is over or underrepresented, and blocking, where we group similar experimental units together, like using the same machine or operator within a group, to reduce noise from known sources of variation. All of these techniques work together to help us design better, fairer, and more informative experiments, which leads to more confident engineering decisions. Let's go over an example together. A manufacturer of paper used for making grocery bags is interested in improving the product's tensile strength. Product engineering believes that tensile strength is a function of the hardwood concentration in the pulp, and that the range of hardwood concentrations of practical interest is between 5 and 20%. A team of engineers responsible for the study decides to investigate 4 levels of hardwood concentration: 5%, 10%, 15%, and 20%. They decide to make up 6 test specimens at each concentration level by using a pilot plant. All 24 specimens are tested on a laboratory tensile tester in random order. The question we need to answer is whether any of these hardwood concentration percentages will lead to a significantly different tensile strength. We start by looking into how we can statistically model such problems. We model the strength of each paper bag samples as yj equals to mu plus ti plus epsilon ij, where yj represent the observed tensile strength for the jth specimen in wood concentration level I. Mu is the overall mean strength across all wood concentration percentages. Ti, the treatment effect of hardwood concentration I, where index I can represent 1/4 wood concentration levels 5%, 10%, 15%, or 20%. Epsilon ij is the random error for the jth specimen under wood concentration I. We could also write yj equals to mu I plus epsilon ij, where mu I equals to mu plus ti. Main assumptions on the error term is that they are independent and follow a normal distribution centered at 0 with a constant variance. This is called a completely randomized design, as each treatment, wood concentration, is assigned to experimental units, paper specimen, at random. The number of observations per group is equal, a balanced design. And all samples are tested under similar conditions, where the only systematic difference is the treatment, hardwood concentration. In this setup, the experimenter has intentionally selected a specific set of treatments to study. These treatments are not randomly chosen from a larger population, they are the only ones we care about. The goal is to compare the treatment means, estimate the effect each treatment has on the response, and test whether at least one treatment effect is different from the others. This situation is described using the fixed effects model. When using a fixed effects model, the results apply only to the treatment studied. We're not trying to generalize to a larger population of treatments, just the specific ones used in the experiment, like for selected types of hardwood concentrations. In the fixed effects model, we are interested in determining whether the different treatments we selected have a meaningful effect on the outcome we're measuring. The null hypothesis states that all treatment effects, ti, are equal to 0, meaning that the treatments have no effect beyond the overall average response. In other words, the differences we observe in the data could just be due to random variation. The alternative hypothesis claims that at least one treatment effect is not 0, which means that at least one treatment produces a different outcome compared to the others. If we reject the null hypothesis, we conclude that not all treatments are equally effective and that the treatment factor does have a statistically significant impact on the response. ANOVA helps us answer a fundamental question. Are the observed differences in group means real, or could they simply be due to random variation? It determines whether the means of multiple groups are significantly different, not by directly comparing the means themselves, but by comparing variances, specifically by comparing between group variation and within group variation. Between group variation measures how much do the group means differ from the overall mean, while within group variation measures how much do individual values differ from the mean of their own group. If the group means are far apart, large between group variation, and each group is internally consistent, small within group variation, then ANOVA concludes that the differences are likely due to the effects of the treatments, and that at least one group mean is significantly different, as shown in case 1. On the other hand, if there's a lot of within-group noise, meaning individuals in the same group vary widely, then even if group means differ a little, it's hard to say the treatment had any real effect, as displayed in case 2. In that case, ANOVA suggests that the observed differences are likely due to random chance rather than meaningful group effects. Let's go back to our example and try to answer whether any of these hardwood concentration percentages will lead to a significantly different tensile strength. This side-by-side visualization illustrates within-group and between-group variation in tensile strength for different hardwood concentrations, which are at the core of what ANOVA measures. But while visuals are powerful for building intuition, they're not enough to draw statistical conclusions. The left plot visualizes the between-group variation. We can see that the group means differ. Some are above the overall mean, purple dotted line. Others are below it. The vertical blue arrows show how far each group's mean is from the overall average. The right plot visualizes the within-group variation. This shows how spread out the individual data points are within each group. Some groups have tightly clustered values, while others, like the 10% group, have wide variation. The vertical blue arrows show the distance between each point and its group's mean. Visualizing between and within group variation, although helpful, is not enough as 1. Visuals don't quantify uncertainty. 2. Visuals can be misleading, and 3. We need a formal decision rule. As we discussed, ANOVA answers the question, are the differences between group means statistically significant? To do this, it partitions the total variation in our data into 2 parts. 1. The treatment variation, which measures differences between group means, and 2. The error variation, which measures differences within groups, random noise. As a result, the total variation in the data, SST, is a summation of sum of squares of treatment between group variability and sum of squared of error within group variability. Looking at the expected values, we can calculate the mean squared of treatment and mean squared error. In other words, we can see the average variability between groups and within groups. Comparing these means, if the mean squared of treatment is significantly larger than mean squared error, we can conclude that the between-group variability is large relative to within-group noise, which suggests that at least one treatment has a significant effect. All the key information from our analysis is summarized in the ANOVA table. As you may recall from our earlier modeling discussions, each observation is influenced by 2 components: the effect of the treatment level, which explains variation between groups, and the random error term, which accounts for variation within groups. In the ANOVA table, the first row captures the variability between the groups caused by different treatment levels. The second row captures the variability within each group caused by random differences. The third row shows the total variability, which is the sum of the between-group and within-group variations. Just like we discussed, the total sum of squares is the combination of the sum of squares due to treatments and the sum of squares due to error. The total degrees of freedom is also the sum of the degrees of freedom for treatments and error. If we have A treatment levels, the degrees of freedom for treatment is a -1. Next, we calculate the mean squares by dividing each sum of squares by its corresponding degrees of freedom. The F statistic is then found by taking the ratio of the treatment mean square to the error mean square. If this ratio is large enough, it suggests that at least one treatment group is significantly different from the others. To make a final conclusion, we can use either the p-value approach or the rejection region approach, just like in any other hypothesis test. Once we set a significance level, alpha, we either compare the p-value to alpha or compare the F statistic to a critical F value, based on alpha, treatment degrees of freedom, and error degrees of freedom. If the F statistic is greater than the critical value, we reject the null hypothesis and conclude that not all treatment levels' impact are equal. In this specific example, we have 4 treatment levels. So, in our null hypotheses, we claim the impact of all 4 concentration levels are equally 0, tie, 1 equals to tie, 2 equals to tie, 3 equals to tie, 4 equals to 0. In order to perform ANOVA manually, we need to find the error and treatment sum of squares. We need to find their degrees of freedom, calculate their mean squares, and report the F-test statistic and its corresponding p-value. Alternatively, we can use a programming language to perform the analysis. Using Python, we would get the reported ANOVA table. Please note that programming languages usually don't report the total row, as it is only a summation of treatment and error sum of squares and degrees of freedom. Here, looking at the ANOVA table, we can claim that at least one of the hardwood concentration levels' impact on tensile strength of the produced bags is significantly different from the other levels. But the problem is that ANOVA can confirm for us that there is at least one significantly different treatment level. It cannot answer how many levels are significantly different, or which levels are significantly different. When an ANOVA test results in a rejected null hypothesis, it tells us that at least one group mean is different, but it doesn't tell us which ones. To answer that question, we use multiple comparisons procedures, and Fisher's LSD method is one of the simplest and most widely used. Fisher's least significant difference, LSD, test is a way to compare all pairs of group means one by one. It tests if the difference between each pair of means is statistically significant using the t-test. The null hypothesis for each pair is that the means of the 2 groups are equal. In a typical t-test, we calculate the test statistic t and compare it to a t-distribution to determine if the difference is significant. In Fisher's LSD method, a pair of means is significantly different if the absolute difference between the 2 means is greater than the LSD value, where the LSD value is computed using the error mean square from the ANOVA, the number of observations, and a t-critical value based on your chosen significance level and degrees of freedom. But because we're running many pairwise comparisons, the chance of making a type 1 error increases. To control for this, we can use the Bonferroni-adjusted LSD, where the significance level, alpha, is adjusted by dividing it by the number of comparisons. This makes the test more conservative, reducing the chance of false positives. Tukey's HSD is a post-hoc test used after ANOVA when we want to find out which specific group means are significantly different from each other. Unlike Fisher's LSD, Tukey's method controls for the overall error rate across all pairwise comparisons. That makes it more conservative and reliable, especially when we're comparing many groups. Tukey's HSD compares every possible pair of group means, just like Fisher's LSD, but it uses a special value from the studentized range distribution, which adjusts for multiple comparisons. This gives us a critical value for the smallest significant difference allowed between 2 means. If the absolute difference between any 2 group means is greater than this HSD value, those 2 groups are considered significantly different. Tukey's HSD is especially useful when we have equal sample sizes, though it works for unequal sizes, too, with slight modifications. We want to compare all groups against each other, not just a few. It helps us control the family-wise error rate, the chance of making one or more type 1 errors across all comparisons. In order to manually perform the Fisher's LSD method at 5%, we need to find the Bonferroni-adjusted LSD value. To do so, first we need to find the number of pairwise comparisons. Given that we have 4 factor levels, we will have a total of 6 pairwise comparisons, 4 times 3 divided by 2. Our adjusted significance level would be 0.05 divided by 6, which is 0.008. Now, we need to retrieve critical t-value for 0.004 with 20 degrees of freedom. Once we have this t-critical value, we can multiply it by square root of 2 times MSE divided by 6, number of observations per group. So, our Bonferroni-adjusted LSD is 4.31. Now we need to compare the absolute mean differences between groups to this adjusted LSD. If the absolute mean difference is bigger, then we would report a significant difference between these treatment levels. As for Tukey's HSD method, we can easily rely on Python to perform these pairwise comparisons. In this table, the columns represent Group 1 and Group 2, the pair of groups being compared, for example, 5% versus 10% hardwood concentration. Mean diff, the difference in mean tensile strength between the two groups. PADJ, the adjusted p-value, accounts for multiple comparisons. Lower and upper, the bounds of the 95% confidence interval for the mean difference. Reject, whether the difference is statistically significant, true equals yes. Looking at Tukey's HSD result, we can report the 5% group is significantly different from all others, 10%, 15%, and 20%. It consistently has lower tensile strength. 10% versus 15% is not significantly different, p equals 0.78, indicating similar performance. All other pairs, 10 versus 20 and 15 versus 20, show statistically significant differences. The final step in analysis of variance is the adequacy check. To ensure we can trust the ANOVA results, we must confirm that the assumptions made about the error term are valid. At a minimum, we need to verify two key conditions: normality of residuals, constant variance, homoscedasticity, across residuals. To check normality, we typically use a normal QQ plot. If the residuals fall approximately along a straight line, the normality assumption is likely satisfied. To assess constant variance, we examine a residuals versus fitted values plot. A good sign is the lack of any clear pattern. In other words, the residuals should appear randomly scattered. If we observe funneling, curvature, or clusters, that may suggest a violation of this assumption. Considering the fixed effects model we defined, we can construct confidence interval around each treatment mean and the mean difference between any given two treatment pair. For the mean of the treatment I, the confidence interval is defined as yi bar plus minus a t-coefficient of 1 minus half alpha with a times and minus 1 degrees of freedom times square root of MSE over n, where a represents the number of levels and n is the replication size. For the confidence interval on the difference in two treatment means, the confidence interval is yi bar minus yj bar plus minus a t-coefficient of 1 minus half alpha with a times and minus 1 degrees of freedom times square root of 2 times MSE over replication size. These confidence intervals are built using MSE from ANOVA. Assuming normality and equal variance, MSE is good estimator for the variance of error term. In a balanced design, each treatment has the same number of observations. But in real-world experiments, some groups might have more or fewer data points. When this happens, we call it an unbalanced design. In an unbalanced experiment, we need to slightly modify the formulas we use to calculate the sums of squares in ANOVA. Instead of treating each group equally, the calculations now take into account how many observations each group has. For the total variability in the data, known as the total sum of squares, we still measure how much all individual data points vary from the overall average, but we do so by summing over the actual number of values in each group. For the variability explained by the treatments, known as the treatment sum of squares, we now weight each group's average by how many data points that group contains. This ensures that larger groups have a proportionate influence on the analysis. Finally, the unexplained variability, error sum of squares, is still found by subtracting the treatment variability from the total, but the key change is that both quantities are now calculated with unequal group sizes in mind. This adjustment ensures that our analysis remains accurate even when our design is unbalanced. Balanced designs are better as such designs provide robustness to assumption violations and maximize statistical power. When sample sizes are equal, ANOVA is more robust to violations of the assumption of equal variances, homoscedasticity. With unequal sample sizes, ANOVA becomes more sensitive to such violations. Also, qual sample sizes give ANOVA more power to detect actual differences between groups. When designing experiments, one of the most important decisions is choosing the sample size, that is, how many observations or replicates to include for each treatment group. The goal is to have enough power to detect real differences when they exist, without making the experiment unnecessarily large or expensive. As a reminder, Power is the probability of correctly rejecting the null hypothesis when it is actually false. In other words, it's the test's ability to detect a real effect. It's calculated as 1 minus type 2 error. As we discussed, we use a f-test statistic to make a conclusion in ANOVA. If the null hypothesis is false, the f-statistic from the ANOVA follows a non-central f-distribution, not the usual central one. The non-centrality parameter, phi squared, depends on the size of the treatment effects, or how different the group means are, the number of replicates, and the variability in the data. An operating characteristic, OC, curve shows the probability of a type 2 error for different values of the effect size and sample size. It helps us decide how many replicates are needed to achieve a desired level of power for detecting differences among group means. In OC curves, the vertical axis shows the probability of failing to reject the null hypothesis, which equals 1 power. The horizontal axis shows different values of phi, the non-centrality parameter, which reflects how strong the treatment effects are relative to noise. Each curved line represents a different value of the error degrees of freedom, nu2, which increases as sample size increases. Two sets of curves are shown. Left plot, 4 treatments, nu1 of 3. Right plot, 5 treatments, nu1 of 4. Each plot has curves for 0.05 and 0.01 significance levels. In analysis of variance, it's important to distinguish between fixed and random factors. A fixed factor refers to a situation where the analysts deliberately select specific levels of a factor to study, such as testing 5 named brands of fertilizer or 3 preset temperatures. The conclusions in this case apply only to those exact levels used in the experiment. In contrast, a random factor is used when the levels included in the experiment are considered a random sample from a much larger population of possible levels. For example, if you randomly select 5 machines out of a fleet of hundreds to test, you're treating the machine as a random factor, and you want results to generalize to all machines, not just the 5 tested. Although the mathematical model for fixed and random effects may look the same, the interpretation is quite different. In a random effects model, the treatment effects are treated as random variables, and the focus is on estimating the variability across all possible levels, not the specific differences between the ones selected. This means the total variation in the response includes both the variation from the treatment effects and the variation due to random error. As a result, the random effects model is especially useful when you're interested in making broad inferences about a larger system or population, rather than just comparing specific groups. Thank you for watching another video on design of experiments and analysis of variance. See you in the next one.